Hi calculus students. This video is on differentiation rules, and differentiation is kind of a new word, so I just first of all want to say what I mean when I say differentiation. So differentiation is the process of taking a derivative or finding the derivative of a function. And so that's a noun, but you could also have a verb form, which is differentiate. Okay, so we're going to see, we started noticing patterns in class, and we're going to I'm going to formalize those patterns for you, and then we're going to see a bunch of examples, and hopefully you're going to be really happy that you no longer have to use the limit definition of the derivative every time you want to differentiate. So the first, I'm going to have a series of rules. The first rule is called the constant rule. So the constant rule is if you have some function that is just a constant, as in a number. So f of x equals c, where c is a number. Well, then if I wanted to know what is f prime of x when f of x is a constant, well, first of all, we can think about it graphically, and that's going to help this make more sense. But if like c is some y value, then the graph of f of x equals c is just a horizontal line through that y value. And so the idea is like, what is the slope of a line, of the tangent line at a point? So like at any point here, you can pick a point, the tangent line is just right along the same line, and the line is horizontal. So what's the slope of that line? It's always going to be 0. Okay? So what is f prime of x here? It's going to be the slope. We know that the slope of f of x will always be 0. So therefore, we get this rule which says f prime of x is always 0 if we have just a number. So that's our first rule. I'm not going to do any examples there because it should be pretty obvious, but it'll kind of come into play potentially in some other examples. So the next rule, this is a rule we figured out in class, is called the power rule. So the power rule is when you have f of x as a variable raised to some power n. And so the key, well, first of all, I want to say that n doesn't have to be an integer. Usually, like, it doesn't have to just be 2, 3, 4. It could also be 1/2 or 0.26. It could be anything. So just want to make a little note. N doesn't have to be an integer. Okay, so then what you guys figured out in class was that the derivative here was you bring the exponent out front, so it would be n times x, and then your new exponent is 1 less than your old exponent, so we'll write that as n minus 1. This is called the power rule. So we're going to be using the power rule all the time in this class moving forward. It's one of the most useful rules. But before I kind of show you some examples, I just want to introduce a new notation, and I'm going to kind of write it off to the side here. So one way of talking about the derivative or writing the derivative is with the f prime, right? Like this type of notation. There's one other way that we could show taking a derivative of something, and it looks like this. It's d over dx, and then after that we'd have like parentheses, and what comes next could be some sort of expression or function here that we want to take the derivative of. So there's some sort of function in here. So we'd say d dx of a function means the derivative with respect to x. And don't worry too much about that kind of with respect to x, but just kind of take this to mean take the derivative of what's in parentheses. Okay, so I'm going to show some examples, and I'm going to be using this new notation, but also still using the f prime notation. And I'm going to kind of switch back and forth, but know that they're the same notations. We're doing the same process, even if the notation is different. So the first example. So f of x is x to the fifth. So if I wanted f prime of x, what would I do? Following this rule, I would move my 5 out front, write my x, and then my new exponent is 1 less than my old, so it's a 4. Okay, so the derivative of x to the fifth is 5x to the fourth. So let's look at another example. I'm going to use the new notation this time. So what if I said d dx of 1 over x to the fifth? Okay, so I say we can still use the power rule here because I can rewrite 1 over x to the fifth as, I'm just going to write my d dx again and rewrite what the function is in a way that we can actually express it as x to a power. And that would be, I know if I have a power in the denominator, I can bring it up to the numerator with a negative exponent. So I know 1 over x to the fifth is the same as x to the negative fifth. Now I can apply the power rule, which says bring the exponent out front, rewrite your x, and then subtract 1 from negative 5. Now be careful here because negative 5 minus 1 is not negative 4, it's negative 6. Okay, so then the derivative of 1 over x to the fifth is negative 5x to the negative 6. Next example. If f of x equals the square root of x. Okay, well, first of all, this doesn't look like x to some power, right? This looks like the square root of x. So how can we actually use the power rule here? Well, you have to remember that square roots can be, or any sort of roots can be written as fractional exponents, as rational exponents. So the square root of x is the same thing as x to the 1/2. And once I have that, I can easily use the power rule to say that the derivative here should be 1/2 x, and then I should subtract 1 from 1/2, and I get negative 1/2. Now, I can leave it with my negative exponent. Actually, both of these have negative exponents, so it's kind of like you can leave it with the negative exponent, or you could rewrite it with the negative exponent in the denominator. So like for this one, I could rewrite this as 1 over 2x, and then I could write it with a 1/2 in the denominator, or I could write it as the square root. So I could bring back the square root. And actually, I'm going to do the same thing to example 2. I'll rewrite it as negative 5x to the 6th. Notice the negative 5 out front, the coefficient, it stayed on in the numerator. Only the x to the 6th got moved down because the negative exponent isn't being applied to the coefficient. It's only being applied to the variable. Okay, let's keep going. My next example, I'm going to use my new notation again. So the derivative of 1 over the cubed root of x squared. So again, this looks not like a variable raised to a power, but I can rewrite it as such. So I'm going to rewrite this with, I'm going to make my cubed root, that's to the 1/3 power. And then if I'm going to move what's in the denominator to the numerator, I need negative exponents. So it looks like a negative x to the negative 2, and then the way we incorporate the cubed root is we do divided by 3 because that's like a 1/3 power being multiplied to the negative 2 that's already there. So now, so this is now the function that I'm taking the derivative of. And when I do that, I bring the negative 2/3 out front. I have my x, and my new exponent is negative 2/3 minus 1. The trick here when you have fractions and you're subtracting 1 would be like you're subtracting from this 3 over 3, which is 1. So really you're just subtracting 3 from the numerator, and that gives me -5, and then it's still over 3. So this is it in rational exponent form, but I could also write it with roots, which would look like the -2 stays where it is, the 3 stays where it is.
Your attention.
Oh, let's wait
Alex,
for this
respond to the
announcement.
front desk. Your food delivery is here. Once again, Alex, respond to the front desk. Food delivery.
Okay, so then we have an x to the 5th, and then the cubed, the like over 3, or I could rewrite it as the cubed root, so I could bring back in that cubed root at the end. So it's -2 over 3 times the cubed root of x to the 5th. And either of these answers would be acceptable. If it's multiple choice, I want you to be able to get it back into the root in case the answers are in root form and not rational exponent form. So best practice is practice getting it back into that form just in case on a multiple choice question you have to. Okay, let's slide this up. I'm going to give you all a practice one. So you try is I want you to find the derivative, d dx, of the square root of x to the 3rd power. So remember, to start, you're going to need to rewrite the square root as a fractional exponent and then go from there. So pause the video, try that one out, and then I'm going to keep going. We have 2 more rules to talk about. So the next rule is called the constant multiple rule. You actually you noticed this rule in class as well. So the constant multiple rule says that if you have some function, I'm going to call g of x this time. There's a reason why I'm saying g instead of f. And g of x is equal to some other function, f of x, multiplied by a constant. So I'm going to represent that by like a c out front. So that's my constant. And it's being multiplied to a function. Then we have a rule that says the derivative here, g prime of x, is exactly that constant times the derivative of the function f of x. So we noticed this when we were kind of sorting through the different examples in class, but let's see how it works. So the idea would be if I'm taking the derivative of something like 3x squared, that is like saying 3 times the function x squared. I can use the power rule for the function of x squared, so I know that the derivative of x squared is bring the 2 out front, write your x, and then my new exponent is 1 less than my old, so 2 minus 1 is 1, so I don't even need to write anything. I'm just going to take that and multiply it by 3. So I just kind of bring the 3 over, so this becomes 6x. Now, you're going to get really quick at this, and you're not necessarily going to write this intermediate step. You're going to look at this and say 2 gets multiplied to 3 and gives me 6x. My new exponent is 1. And you can kind of skip this intermediate step. Let's look at another example. So my next example is if f of x equals 2 over, say, x to the 2nd. Well, we'll say x to the 3rd, make it a little different. So then what is f prime of x? It would be, well, before I get to my derivative, let's rewrite this as 2 times x to the -3. So now I can see, oh, I need to bring the -3 out front. So it's going to be 2 times -3, which is -6, times x to, what's my new power? It's -3 minus 1, so it's -4. And then I could also rewrite that so that I move my exponent to the denominator, and that would look like -6 over x to the 4th. So I'm going to give you all one to try. So you're going to try the derivative of 1/2 x to the 4th power. So pause the video, give it a shot, and I'm going to keep going. So the last thing we're going to talk about is something called the sum and difference rules. And they're basically the same rule, except one's for addition and one's for subtraction. But the idea would be if we have some function h of x, which is the sum or difference of two other functions, or even three, or however many, infinitely many, I guess. We'll keep going. So if we have like f of x plus or minus d of x, then the derivative of the sum or of the difference will be exactly, oh, I didn't mean to write that. Then we have h prime of x is equal to f prime of x plus g prime of x. So what that means is we can take derivatives of more complicated polynomials. So we could have something like f of x is 4x to the 5th minus 3x to the 6th plus 2x to the 3rd. And then if I wanted to take the derivative, I just take it one term at a time. So the derivative of 4x to the 5th means, now notice we're like combining three rules at once here because this is a constant times a power, right? So we're going to use the power rule here and then multiply it by the constant. So I end up with 5 gets multiplied to 4 and gives me 20 x. And then my new exponent is 1 less than my old, 4. So it's 20x to the 4th. With my next one, 6 is getting multiplied to 3. I'm going to bring down the negative sign, so I get 18x. And then my exponent gets bumped down 1 to a 5. So negative 18x to the 5th. And then my last term would be 2 times 3. The 3 comes down, so I get 6x. And my new exponent is 1 less than my old, 2. So let's look at another example that's just has a little bit more tricky terms. So I'm going to use my new notation this time and do 2 times the square root of x plus 1 over x to the 2/3 minus 6 times the cubed root of x plus 3/4 x to the 4th. Okay, so now that might look a lot scarier than example 7, but we can really take it like one term at a time and think about what we need to do for each term. So I'm going to do a little bit of rewriting here before I take the derivative, but 2 times the square root of x, I'd rather write that as 2 times x to the 1/2. 1 over x to the 2/3, I'd rather write as x to the negative 2/3. Minus 6, the cubed root, I'd rather write as x to the 1/3. And I'll just bring down that last term. That's fine. Okay, so now this is what I'm taking the derivative of. Okay, so what happens? Well, with my first term, the 1/2 comes out front. It gets multiplied by the 2. 2 times 1/2 is just 1. So I'm left with an x with like a, you can put the 1 there, but you don't have to. And then my new exponent would be 1/2 minus 1, negative 1/2. Plus, here I don't have any coefficient out front, so I'm just going to bring down my negative 2/3. X to the, my new exponent should be 1 less than this, so I'd subtract 3 from my numerator. I get negative 5 x to the 3rd, or negative 5 over 3, sorry. And then my next term, I'm subtracting. I'm doing 6 times 1/3, so 1/3 comes out front, so that becomes a 2x, and then my new exponent would be 1/3 minus 1, or 1/3 minus 3/3, so that would be negative 2/3. And finally, my last term would be, I'm going to bring my 4 down, so it's 4 times 3/4. Well, really quick off to the side, 4 times 3/4, the 4's cancel, so you just have a 3. X to the, and then 4 minus 1, 3. Okay, so this right here represents my derivative. Notice I no longer have the d dx out front because now this is the derivative, but I would like to rewrite some of these terms so I don't have negative exponents and I don't have fractional exponents and I instead have roots. So for the first one, it would be 1 over the square root of x. For the second one, it's going to be minus, so if we think about what's going on here, the denominator of 3 means the cubed root. The 5 is an exponent of 5, but it's also negative, which means sorry about that, guys. My video just cut out. It's had some technical difficulties, but okay, let me recap what went on right here. So the negative meant it went down to the denominator. The denominator of 3 and the exponent meant it became a cubed root, and the 5 stayed as an exponent. So that's this term. So for my next term, I get minus, the 2 stays on top. X squared stays x squared, but then the denominator of 3 becomes the cubed root. And then my last term stays 3x to the third. Okay. So it gets to be a lot, right? There's like, you have to be careful when you do this, but it's a lot easier than if we had to use the limit definition of the derivative to get this, and then the limit definition of the derivative to get that, and then the limit definition of the derivative to get this term, and that would take a super long time. So we are really going much faster now through calculating derivatives. So to close out the video, I'm just going to give you one last u-try problem. So if f of x equals 1/2 x squared plus 6x minus 7x to the 3/5 minus 4 over the 4th root of x. Okay, so give that a shot. Be careful. Think about what rules you're following, and you'll be practicing this in class on Monday.